know it's been a while since the first episode, but please understand, there's a finite amount of time I can work on these. Plus, I'm not always in the right state of mind to want to work on them. I'm not exactly a well-oiled machine, after all. Regardless, today I'm going to cover the topic that I so hand-fistedly inserted into my opening dialogue. For the uninitiated, a finite state machine, or FSM for short, is a great way of handling behavior for a given entity, allowing for separate and different implementation depending on the scenario. Wikipedia defines an FSM as a list of its states, its initial state, and the conditions for each transition. As a result, an entity can only be in one state at a time, which makes sense. This way your character won't be both jumping and swimming, or walking and running. For my purposes, this is all I need, but sometimes you want to have multiple, unrelated states occurring at the same time. You can accomplish this usually through hierarchical or concurrent state machines. I use state machines for pretty much all entities in my game, for better or for worse. The entities it works really well for are the game controller itself, the camera, the player, and the enemies for the most part. For things like items though, it just kind of feels like unnecessary clutter. Before I get into it, my implementation of the state machine is needlessly complex and hopelessly over-engineered. So this isn't really something to base off of, but rather learn from. That being said, I still deem it interesting enough to talk about. To begin, I've got 3 classes and 1 interface that need to be understood before anybody can make any sense of what I have to say, namely the classes state machine, state, data, and the interface iState. The state machine class derives from monobehavior, and is the component that actually goes on objects. As such, it contains a list of generic iState interfaces, which are what actually encompass the behavior of the object. Like previously described, it just controls which behavior the object exhibits. iState has a get property of the generic type, and 4 functions, all of which are pretty self-explanatory. setFSM, initialize, update, and deinitialize. The coolest thing about this interface is it takes advantage of some of the features in .NET 4. As I mentioned, it's a generic interface, but it's also covariant, and it constrains the generic type to data. From my very limited understanding, variance basically takes advantage of implicit casting. Covariance, what I'm using, allows you to downcast an interface, so to speak, to another whose generic type derives from the other interface's generic type. However, there is a catch. The type can only be received through that interface, which means no setters or parameters of the generic type. I know I probably did a terrible job explaining, but it's fascinating and definitely worth reading about. Though it has seemingly few applications, I saw a potential use for it in my FSM implementation. Essentially, what it allows me to do is share state functionality across entities that derive from the same parent. Going back to my data class, it's a child of scriptable objects. Without getting too sidetracked, scriptable objects allow you to package data without a prefab. In Vinci Game, there are several different types of data, one for each step in the hierarchy, each containing non-physical information for that entity. For example, every character has a health value, but only enemies will have experience that they reward the player. Now the reason for the generic type in iState may be coming to light. I'm able to access the most specific type of data in classes that implement the interface, while still being able to store a list of iState interfaces with generic type data in the state machine. The state class abstractly implements the iState interface for the most part, and is also generic. The only difference is, it implements setFSM to set the state machine variable, and the property to get the data for the state. Several abstract child classes then inherit from the state class explicitly setting the generic to whatever type of data fits the state being implemented, i.e., the character state has a generic of type character data. Finally, specific behaviors are written that derive from these abstract classes, and these are the states that get assigned to the state machine itself. Well, that got a little more technical and in-depth than I had initially intended. Another short one, but I think I should just about wrap up the second episode of my Development Diary series. Thanks for watching.